All right, so in my last video, I showed how to use the imitation learning recorder, record players' actions, record NPCs' actions, feed those into a neural network, and train a neural network to output variables that then you could use to make an agent take various actions. And in this video, what I wanted to show is how you would integrate that neural network output into an existing behavior tree based agent to kind of get the best of both worlds of combining behavior trees with neural networks. So why would you want to combine those two things? And I'd say there's a few reasons, but the biggest one is that behavior trees are really good at kind of setting high level directives of like, what should I be doing at a high level? So this is an example in my game of the base behavior tree that literally every agent runs, whether it fights with a sword or with claws, whether it's very aggressive, very defensive. Um, they all run this at a high level. And there's a few behaviors I'll give examples of here that it would be really kind of silly to train a neural network to do. So one is, for example, the monster's leash, if they have an anchor point set. So when a monster is spawned, uh, depending on the situation, if it's like in a dungeon, the anchor point will be set and a leash distance will be set. And if they're too far from their anchor point, they turn around and run back home and health regen. And I don't want to train a learning agent to like learn to leash. That just sounds like a lot of work for not a lot of benefit. The neural network can do that just fine. And if I did want to train it, it might be more about like how it runs back or like what it looks like while it's running. I don't know. It wouldn't be necessarily when to leash. That's more of a rule of the game, not a learned behavior. This is another example to save CPU. This is like they basically go into a sleep mode if there's no one nearby to fight. Again, I wouldn't want to train a neural network to do that. It wouldn't make a lot of sense to try and like punish them for using CPU when they can't really change how much CPU. I mean, it just doesn't make sense. So behavior trees are really great for high level kind of goal setting. And then where you might inject a neural network based decision would be somewhere further down the tree. So say I've trained an AI to really attack in a human-like way when it's, fainting, moving, whatnot. I could inject that behavior into the, behavior, the kind of dynamic attacking routine. And so these nodes call dynamic subtrees that individual classes of enemies can set for themselves. I actually don't use the dynamic behaviors that much. It's mostly for bosses with special abilities to do that. Most of the enemies are using a very simple basic attacking tree and basic uh, defending tree. And there's kind of a few core tasks that are called within deeper subtrees that are related to what you should do when you're attacking. And you know, all the agents have a component that I've made that's called a parameters component, that I call an AI parameters component that kind of says what you should do when various tasks are called. So, this is kind of managing an attack. This is picking how far away you want to be when you're swinging. This is should you just decide not to block. This is what direction you should block, uh, stuff like that. And so today, what we're going to be doing is setting up a learn neural network, the one we trained last time, that kind of chose which direction to block, and overriding this choose block direction function to instead block in the direction the neural network suggested we should. And this is the base class. So this is the very default behavior, and it's very very simple here. Basically, agents can have a chance to block the wrong way. Randomly, they either block the wrong way and pick a random direction to block, or they kind of pick the right direction to block and block properly. Obviously, that doesn't give a very realistic feeling of behavior. They don't fail blocking when their opponent does something tricky. They just randomly mess up. Even with that, we'll be able to create a lot of kind of unique behavior. And at a high level, I'd say if you're not in a state where your behavior trees allow you to inject different behavior easily, it's going to be hard to have a learning network inject behavior. And so I did want to give a quick demo of non-learning behavior here that is already injected in game. So this is a little area I've been working on this part of the tutorial. I haven't fully skinned this part yet, and one of my plugins doesn't have an update for 5.3, so the ground here is all messed up. But this spawns a guy who dynamically gets tougher and tougher to hit as you fight him. So at the start, he mostly just stands there. He'll block occasionally. He's fucking pretty good right now. But mostly he walks the wrong way or stands there. He doesn't run away. But as you deal damage to him, he'll get tougher. And so the first increase isn't too noticeable, but every 100 damage he's going to get tougher. He still doesn't know about kicking, so I can still kick him, but he's going to be actually fairly hard to hit with regular swings once he gets one more difficulty level up. And for new players, even this difficulty is already fairly hard to hit him with. You have to start mixing up your attacks. And this is all one behavior tree just being dynamically changed at runtime. Sorry, the music's a little bit loud. All right, so you get the idea. So if you aren't in a position where your behavior trees are set up to allow you to do something like that, where you change the difficulty of your, agent in real time, it may be a little tricky to adjust your, behavior to read from neural networks and potentially swap the network, stuff like that. So I think that following this plan does require that you have a nice clean modular behavior tree setup. I'm not going to make this video about, ending behavior tree spaghetti. I know there's a ton of spaghetti out there. If you guys want something like that, I'm happy to detail, at least share my experience and share what I did in a lot more detail than I did in this video. In a future one, you can leave a comment to that effect, but I'm just going to focus on how do we get a neural network to replace this choose block direction function and block the way the neural network that we trained in the previous video tells us to block. Okay, so let me show you guys how I set this up. So there's a few steps we're going to need to do. The first is that we're going to want to have something to actually manage the neural network itself. And so the way I went about doing that is I made a new actor, and you would have one of these in your level. The reason to have an actor that's kind of a singleton like this, rather than say having each, of your enemy AIs running their own neural network, is purely for optimization. The learning manager base class that this inherits from, learning agents manager, is designed to have one neural network that feeds a whole bunch of agents potentially. And so it's going to be more efficient to just have that one network. Remember, a network is just mapping a set of inputs to a set of outputs kind of blindly. So we can have the same network. Each agent will give it its observations and get out its outputs. We don't want to be running a whole bunch of them for no reason. So that is going to be step one, is we're going to need to have our inference manager. That's going to be super simple and, basically like what we set up last time. So if you recall from last time, we had to set up an interactor and a policy. We're going to do basically the same thing. Pull that up. So I call this one inference manager blocking. And the initial setup is going to be identical. We're going to set up an interactor and a policy. I'm using a different interactor component because we aren't going to actually be executing actions on the agent. We're just going to be storing the variables. I'll show what that looks like next. But for now, if you were following along, you could just make a new component that, of child class of the one from the previous video, and we'll edit it from there. So we set up our interactor, we set up our policy with that interactor. I'm feeding it in the imitation network that we trained just a little bit last time. And then I changed the on tick a little bit. So all it does, no, sorry, this is unchanged. All this does is run inference. So this is obviously super simple. The one thing I took out of the begin play is I took out enabling the actor tick. So this starts with the tick disabled and it's off. The reason I did this is I don't want to be running the network if there's no agents using it. And so what will happen is when agents are spawned, they can choose to register themselves with the network. And if they elect to do so, that'll turn the tick on, and then it'll add them as an agent. Probably it would be better to do this at the end after adding an agent. So that, just in case it like ticks in the middle of adding them or something. Okay. And then this function takes in a the NPC that wants to be an agent using this neural network, and it sends back a reference to the agent that called it. It sends back a reference to our interactor and an agent ID. You probably don't have to do that, but I thought it just might be helpful for the basic enemy class to have that at some point. So super simple. That's all we do here. Then this component is going to be exactly the same. So I made it inherit from the interactor that we used for the purposes of training. It's exactly the same for observations, and it's exactly the same for setting up the actions. But when we get actions, rather than using the neural network directly to decide a direction to block, all we're going to do is I made a function called this that basically sends update agent block data, that basically sends the outputs of the neural network. So this is the output number 1, this is output number 2. It gets them for the given agent, and it sends them to that agent. And that agent could do whatever he wants with them. He could ignore them, he could use them to block, whatever. So this function is now on our agent, and it takes its AI params component and passes the information in there. And then for now, I just assume that if we're getting neural network data, we want to use it to block, and that's a Boolean I set. And here I thought I'd show a quick example. I don't think you need to do this in my use case, but one thing I'd mentioned last time is that it's possible an agent would want to smooth out the inputs from a neural network. So this would be a really simple way to do that, is rather than using the raw value of what the neural network gave us on the current tick, we could do some kind of weighted moving average of what it's given us in the last few ticks. My current example here would run about the same without this, but there might be cases where this would be a helpful thing to do. So I just thought I'd show the technique. They have a built-in function that does it for you, so it's super simple. You just put in, what you got from the network this round, what your last average was, what weight you want to give the new sample, and then set it. And finally, if we go back to our choose block direction function, all this does is it says if we're using the neural network to get the variables we just set, this converts the outputs of the neural network to my enum that says which direction to block, and now we block that direction. And so that we could see it working, I went ahead and logged this direction. And if you recall from the last video, we trained this network very minimally, so it's not going to block particularly well. In a lot of cases, that might be what you want. So I put this on my easy enemy. This is supposed to be someone that a fairly new player could beat, but it's also not supposed to feel like it's just standing there doing nothing. It's supposed to feel like a real opponent. And so what we'd expect to see, if this all works, is we'd expect to see that when we spawn an agent that does this, he's using this behavior tree routine. He's often not blocking, he's attacking, behaving as the behavior tree normally would do. But when he decides to actually block, he'll be picking his direction based on this, and we should see an output of what direction he's blocking. Whereas if he did it without a neural network, we'd see no output. It just would pick a direction. So the last step would then be to, actually put an agent in that's going to do this. So in my basic enemy, there is a Boolean on should use neural network that I added. And I made this like a config variable that you can expose on spawn. And in my begin play, I just said that if that's true, we'll enable the neural network, which involves getting a reference to the inference blocking manager that we made initially, calling register agent, passing in ourselves, and then we're storing these, but they're not currently being used. So very straightforward. This is a little wrapper class that just spawns enemies. So this is going to spawn an enemy after 5 seconds. So we can click play and see what this actually looks like. Okay, so there he is. He spawned in. If we look at our behavior tree, we can see that he's executing the tree and attacking, as we expect. And if we go to attack a direction, we can see he blocked the right way, and we can see the logging, so we know he's using our function. Blocked the right way that time too. He kind of switched his block to be correct after a second there. Right now I'm doing pretty simple stuff. Oops, sorry, click out the window. I'll try fainting and see if that confuses him. Yeah, that confused him when I switched directions there. Again, yeah, that confused him again. So honestly, he seems pretty reasonable for a beginner level AI here. He makes some mistakes, and I think it's actually already probably better than the just randomly making a mistake kind of thing. It seems like when I do something simple, he's more likely to respond correctly than when I do something a little tricky. So I will leave it at that, and thanks for watching.